Hey there, cosmic dreamers, and welcome to Hafee Sleep. Whether you're just tuning in to unwind after a long day, or you're drifting off into a peaceful slumber with us, we're so incredibly glad you're here. Tonight, we're going on a journey together, far away from the comfort of our beds, out beyond the moon, past the planets, and into the deep, silent black between the stars. We're going to chase a mystery, a strange, silent visitor that passed through our solar system, leaving a trail of questions in its wake. This is the story of our first interstellar guest, a scout from a distant sun, the enigmatic Oumuamua. So get comfortable, close your eyes, and let your imagination soar. And before we begin our adventure, if these stories of the cosmos help you relax and explore the universe from right where you are, please consider subscribing to the channel and hitting that like button. It truly helps us grow this little community of stargazers and dreamers. I'm also so curious to know where in the world you're listening from and what time it is for you. Are you cozying up for the night? Or is it the early hours of the morning? Let me know in the comments below. I love reading every single one and feeling connected to this far-flung Hafee Sleep family. All right, settle in. Let's begin. Imagine, if you will, the vast, silent ocean of space. For centuries, we've gazed up at this ocean from our little island, the Earth, wondering if we were alone. We've looked at the stars, those distant suns, and pondered what or who might be orbiting them. We've sent out messages in bottles, radio signals streaming into the void, and built mighty telescopes to scan the cosmic horizons for any sign of a reply. For the longest time, the deep space between stars was just that, empty, dark, and silent. We assumed any visitors from these unimaginable distances would be dramatic, unmistakable, perhaps even intentional. We never expected the first messenger to be so subtle, so enigmatic, and so small. We never imagined it would be a quiet, tumbling, cosmic iceberg passing through our backyard so quickly that we almost missed it entirely. Yet, that is precisely what happened in the autumn of 2017. This is the story of that messenger, the first known visitor from another star. This is the story of Oumuamua. Our story begins on a mountaintop in Hawaii. The Hawaiian Islands are themselves the peaks of immense volcanic mountains rising from the deep ocean floor. On the summit of one of these mountains, Haleakala, sits a remarkable sentinel, the Pan-STARRS telescope. Pan-STARRS, which stands for the Panoramic Survey Telescope and Rapid Response System, is essentially a giant digital camera for the sky. Its job is to constantly scan the heavens, night after night, taking pictures of vast swathes of the cosmos. It's looking for anything that moves or changes. Primarily, it's a guardian, designed to spot near-Earth asteroids that might pose a potential threat to our planet. But on October 19th, 2017, it found something infinitely stranger. On that evening, a postdoctoral researcher named Robert Warwick was doing what he did every day, meticulously comparing the telescope's most recent images of the sky with those taken previously. Now, let's really put ourselves in Robert Warwick's shoes for a moment. Imagine his workspace, probably a desk with multiple computer monitors, the glow of the screens, the main light in the room. The job of sifting through astronomical data isn't always the glamorous, telescope-peering adventure people might imagine. It's often a meticulous, patient process of comparison, a digital treasure hunt. Every night, the Pan-STARRS telescope, that powerful eye on the sky, captures enormous, high-resolution pictures of specific patches of the heavens. The next night, it does
images. The magic and the hard work lies in comparing these two sets of images.
This is a process called blinking. Warwick would have software that allows him to rapidly switch back and forth between the image from one night and the image of the same star field from the next. Stars and galaxies, being so incredibly far away, don't move in any noticeable way from one night to the next. They are fixed, constant. They remain perfectly still. So when you blink the images, the unmoving stars and galaxies just sit there, unchanging. But every once in a while, something does move. A tiny point of light will seem to jump from one position to another between the two nights. That's your target. That jumping dot is almost certainly an object within our own solar system, an asteroid or a comet. Because they are close enough to us that their orbital motion around the sun becomes apparent against the static backdrop of the distant stars. They are the moving specks in the vast, still painting of the night sky. Most of the time, these moving objects are routine. They get logged, their orbits are calculated, and they are added to the ever-growing catalog of known solar system inhabitants. It's important work, like taking a census of our neighborhood. But on that evening, October 19th, 2017, one of those jumping dots didn't behave in a routine way at all. It was a tiny, faint speck, easy to miss if you weren't paying incredibly close attention. But Warwick was, and he noticed two things immediately. First, the jump was big. The distance this object had moved relative to the stars in a single day was huge. This is a major clue. Think of it like this. If you're driving down a highway, the fence posts right next to the road zip past you in a blur because they're close. But the distant mountains on the horizon seem to move very slowly. It's the same effect, called parallax. An object that moves a lot against the starry background from one night to the next must be very close to Earth, just like that nearby fence post. So, Varrick's first thought would have been, "Whoa, this thing is really booking it, and it must be very close." But then came the second, and far more important, observation. It wasn't just the amount of movement that was strange, it was the direction. By plotting its position on the first night and its new position on the second night, you can draw a line. This gives you a rough idea of its trajectory, the path it's cutting across the sky. The vast majority of asteroids and comets in our solar system orbit the sun in roughly the same plane, a flat disk much like the rings of Saturn. This is called the ecliptic plane. The planets all orbit within this same general flat neighborhood. So, when we see a moving object from our solar system, its path across our sky usually reflects this. It tends to move in a way that is predictable and aligned with this plane. Oumuamua's path was completely off script. It was like it came screaming down from high above this flat plane, did a sharp dive right through the middle of the solar system's busy downtown, and was now rocketing back out on a trajectory that was wildly different from anything that belonged here. It was an outsider cutting through the local traffic without following any of the road rules. This is the moment where a researcher's curiosity shifts from routine cataloging to genuine excitement. This was an anomaly, a puzzle. The first thing any good scientist does when they find a puzzle is to gather more data. Warwick, no doubt with a growing sense of intrigue, went back to the Pan-STARRS data from the night before the one he was just looking at. And there it was, the same faint dot in the predicted location, confirming the object was real and its motion was consistent. Now he had 3 data points over 3 nights. This allowed for a much more precise calculation of its path, and the more precise it became, the weirder it looked. But 3 points are good, but more are better. This is where his next move was so brilliantly crucial. He didn't just rely on his own telescope's data, he thought to check the archives of other sky surveys. The Catalina Sky Survey in Arizona is another Sentinel, another telescope system with a similar mission to scan the skies for moving objects. Their data is publicly available to astronomers. So, Warwick, acting on a hunch, searched through the Catalina archives for the same patch of sky from a few days before Pan-STARRS had even spotted it. This is like going back in time. And bingo, there it was. A faint, previously unnoticed speck in the Catalina data from October 14th. It was like finding a hidden clue in an investigation. Now, he had a golden chain of observations. He had data points from Catalina on the 14th and from Pan-STARRS on the 17th, 18th, and 19th. By linking these 4 observations together, spread over 5 days, he could draw a very, very accurate line across the sky. He could project that line backwards to see where it had come from, and forwards to see where it was going. And when he and his colleagues ran the complex orbital calculations, the result must have been absolutely mind-bending. The math didn't lie. The numbers spat out a single, inescapable conclusion that would have made his heart skip a beat. This object was not on a closed elliptical orbit around our sun. It wasn't from the outer solar system, like the Kuiper belt or the Oort cloud, which are still part of our sun's gravitational family. No. This object was on a hyperbolic orbit. Let's break down what that means in simple terms. Imagine the sun's gravity is like a well, and every planet and comet is a marble rolling around and around the sides of that well, trapped in its gravitational pull. Even comets with incredibly long, looping orbits are still just going around and around the well. A hyperbolic orbit is different. It's like a marble that comes flying in from outer space, skims the very edge of the well, gets a slight gravitational tug that changes its direction slightly, and then flies right back out of the well, never to return. It has too much speed, too much energy to be captured. It's just passing through. That was the path. Oumuamua was a traveler. It was not a citizen of our solar system. It was a tourist on a flyby visit. It had entered our solar system from interstellar space, above the flat plane of the ecliptic, and it was now on its way out, destined to disappear back into the blackness between the stars. The sheer velocity it had when it arrived confirmed this. It was moving so fast that the sun's gravity, while it definitely pulled on it and bent its path into a curve, could never hope to hold on to it. It was like a stone skimming across a pond, touching the surface for just a moment before skipping away again. This was the revelation. That tiny, faint dot wasn't just another rock. It was a rock from another star. It was the first concrete proof that objects from other star systems not only exist, but can travel through our own cosmic backyard. It was a moment that changed astronomy forever, and it all started with the sharp eyes and diligent work of a researcher doing his daily job, who knew that a tiny jumping dot was trying to tell him an extraordinary story. It needed a name. The official designation from the International Astronomical Union was a mouthful, 1I 2017 U1. The I stood for Interstellar, and the 1 marked it as the very first of its kind. But the team that discovered it at Pan-STARRS wanted something more poetic. They turned to the Hawaiian language, a nod to the land that hosts their telescope. They chose the name Oumuamua, pronounced Oumuamua. It's a beautiful and deeply meaningful name. It roughly translates to a messenger from afar arriving first, or Scout. It perfectly captured the momentous nature of the discovery. This was our first Scout, our first messenger from the galactic depths. So, we've found our visitor, and we know it's just passing through. The immediate, thrilling question that follows is the most natural one in the world. Where are you from? It's the question you'd ask any stranger who arrived on your doorstep from a long journey. For astronomers, answering this question became an urgent puzzle to solve. They had a map of its journey through our solar system, a precise line drawn across the sky. The logical next step was to simply extend that line backwards, out past the orbit of Neptune, past the fringes of the Kuiper Belt, beyond the hypothetical Oort cloud, and right out of the solar system entirely, into the great galactic beyond. And when they did this mathematical reverse engineering, the line pointed, quite elegantly, towards the constellation of Lyra. Now Lyra is a beautiful and famous little constellation, often depicted as a celestial harp, and it contains one of the brightest stars in our entire night sky, Vega. This immediately captured everyone's imagination. The idea was almost too perfect to be true. A mysterious, seemingly artificial-looking object, as some early speculations went, arrives from the direction of one of the most prominent stars in our sky, a star that has been featured in countless works of science fiction, most famously in Carl Sagan's Contact. It felt like a sign. It was a romantic, almost poetic notion. Our first interstellar visitor, a scout from the Vega system. The story wrote itself. But here's where we have to apply a little bit of scientific reality, and where the true, mind-boggling nature of our galaxy reveals itself. Space, you see, is not a static stage where stars are simply fixed points of light. That's an illusion created by our brief human lifespans. In reality, our galaxy is a swirling, dynamic, chaotic dance of hundreds of billions of stars, all moving at incredible speeds, like a vast school of fish in a dark ocean. The geometry is deceitful because everything is in motion, and we are seeing everything from a moving platform, our own sun, which is itself orbiting the center of the Milky Way at a breathtaking 220 kilometers per second. Let's break this down. When we say Oumuamua came from the direction of Vega, what we mean is that if you could freeze the entire galaxy in place for a moment, draw a straight line from the sun backwards along Oumuamua's incoming path, that line would point very close to where Vega is located right now. But the key phrase is, freeze the galaxy. We can't do that. The galaxy hasn't been frozen. Oumuamua's journey was not a short trip, based on its staggering speed when it entered our solar system, about 26 kilometers per second, or nearly 60,000 miles per hour, relative to the sun. And the fact that it was likely drifting through the empty void for most of that time, astronomers estimated it had been traveling for hundreds of millions of years, perhaps even longer. That's an almost incomprehensible amount of time. Now let's talk about Vega. During that same immense stretch of time, those hundreds of millions of years, Vega has not been sitting still, waiting for a package to arrive. Oh no. Vega, like our sun, is on its own orbital path around the galactic center. It's moving at a different speed and in a different direction. Think of it like this. Imagine you're standing on a sidewalk and you see a car drive past you. You note the direction it came from, which is, say, the direction of your favorite coffee shop 10 blocks away. But if you decide that the car must have started its journey at that coffee shop, you'd be making a big assumption. The car could have turned onto that street from any number of side streets, or even from a highway miles away. you're only seeing a tiny snapshot of its entire journey. Now, scale that up to a galactic level. Vega is that coffee shop, Oumuamua is the car, and the hundreds of millions of years is the time it took the car to drive those 10 blocks. In that time, the coffee shop itself wouldn't have stayed in the same place. The entire city is shifting and moving. This is the concept of proper motion, the actual movement of stars through space relative to the sun. When astronomers did the far more complex math, taking into account the motions of both Oumuamua and Vega over these epic timescales, they realized a crucial fact. Vega was nowhere near the position it's in now, back when Oumuamua would have been in its neighborhood. In fact, for Oumuamua to have originated from the Vega system, it would have had to be ejected from there at a speed that defies physics. It's a physical impossibility. So while the "from the direction of Vega" line is a useful and true initial shorthand, it's not the object's return address. This realization leads us to a profoundly humbling and, yes, lonely thought. We can trace Oumuamua's path back out of our solar system with great precision. We can identify a general region of space it came from. But pinpointing its exact parent star? That is a task that is likely forever beyond us. Its precise point of origin is lost to the immense yawning stretches of space and time. It is a cosmic orphan. For perhaps over 1 billion years, this strange, tumbling shard of something has been adrift. It has been utterly alone, a silent ship sailing through the most empty and desolate environment imaginable, the interstellar void. Try to picture its journey. After whatever violent event launched it, a colossal impact on a distant exoplanet, a gravitational kick from a passing star, the chaotic upheaval of its native solar system's youth, it was cast out. It spent eons in total blackness. The temperatures out there are just a few degrees above absolute zero, the coldest anything can be. It was bathed in the faint, eerie glow of distant, unchanging stars. It was peppered by cosmic rays, high-energy particles that likely altered its very chemistry over millions of years. It passed through clouds of interstellar dust. It witnessed the slow, majestic rotation of the galaxy's spiral arms. It was a journey of unimaginable duration and isolation, all without a whisper, without a single witness. And then, for the briefest of moments, its lonely path intersected with ours. It dove through our home system, a place teeming with warmth, light, and life. It came closer to our sun than the planet Mercury does. It passed within a stone's throw of our own world, in cosmic terms. For a few short weeks, it was the most intensely studied object in the solar system, the subject of wonder, debate, and fascination for our entire species. And then, just as quickly as it arrived, it was gone. It sped back out into the darkness from whence it came, carrying with it the secrets of its origin, forever silent. So while we may never know the name of Oumuamua's parent star, its visit taught us something perhaps more valuable. It taught us that the building blocks of planetary systems are not confined to their own stars. The galaxy is apparently filled with these drifting nomads, these free-floating messengers carrying the history of other worlds. Oumuamua's origin is a mystery, but its very existence is a revelation. It's proof that the cosmos is connected, that material from around one star can, and does, travel to another, potentially even seeding the raw ingredients for life across the vast interstellar distances. It came from somewhere out there in the great starry ocean, a silent testament to the fact that even in the immense emptiness of space, nothing is ever truly an island. Now let's really picture this grand tour, this incredible journey that our silent guest took through our home system. It's a story of unbelievable speed, celestial mechanics, and a touch of cosmic irony that we almost missed it entirely. To understand its path, we have to think about gravity not as a simple pull, but as a sculptor of motion, a master of celestial slingshots. Imagine the solar system not as a flat disk with neat circles, but as a vast, three-dimensional gravity well, a kind of cosmic valley with the sun sitting at the very bottom, the lowest point. The planets are all rolling around in this valley, each in their own carved-out track. Now picture Oumuamua not as something from within this valley, but as a hiker coming from a distant mountain range, another star walking along a high ridge. It's moving with a certain speed and direction, minding its own business, when suddenly it steps off the ridge and into the steep slope of our sun's gravity well. The moment it crossed the invisible boundary, where our sun's gravity became the dominant force pulling on it, it began to accelerate. This wasn't a gentle pull. It was a tremendous, relentless tug. Think of it like a roller coaster car being dragged up that first enormous hill by a chain, storing up potential energy. But in this case, the chain is gravity itself, and the hill is the sheer gravitational influence of the sun. Oumuamua was pulled inward, faster and faster, building up speed as it fell toward the heart of our system. This is a fundamental rule of gravity. As an object falls toward a massive body, it trades height for speed, potential energy for kinetic energy. It was in a race, and the finish line was the sun. The climax of this race, the point of its closest approach to the sun, is called perihelion. This happened on September 9th, 2017, and the numbers involved are so staggering they are almost hard to comprehend. On that day, this little object was moving at nearly 88 kilometers per second. To put that in perspective, that's about 196,000 miles per hour. Our fastest ever human-made spacecraft, the Parker Solar Probe, on its closest dives toward the sun, hits speeds around 430,000 miles per hour, but it uses massive planetary gravity assists and powerful rockets to do it. Oumuamua was achieving this speed purely through the sun's gravitational pull. It was moving so fast it could have traveled from the Earth to the Moon in less than 2 hours. At that velocity, it wasn't just orbiting the sun, it was screaming past it in a ferocious, high-speed dive. It passed within 23 million miles of the sun's fiery surface. To understand how close that is, let's look at our solar system's innermost planet, Mercury. Mercury's average distance from the sun is about 36 million miles. So Oumuamua dove deep into Mercury's orbit, getting closer to the sun than that planet ever does. It was right in the hot zone. The temperature on its sun-facing side would have been scorching, hot enough to not just melt, but to vaporize many metals and rocks. For a comet made of ice, this would have been an utterly violent experience, causing explosive outgassing, even for a rocky or nitrogenous object. This was an extreme bake-off, a trial by fire that would have significantly altered its surface, perhaps cracking it, baking it, and changing its chemistry forever. It got a front-row seat to the most powerful force in our neighborhood, and it paid the price in heat and radiation. But here's where the roller coaster analogy completes its loop. You know that feeling when you crest the top of the first hill on a roller coaster and you plummet down. But then the coaster uses all that built-up speed to hurtle you up and over the next hill. That's exactly what happened to Oumuamua, but in a much more dramatic fashion. It didn't have enough energy to go over the next hill and stay in orbit. It had way too much. It shot past the sun at its incredible speed, and then it began the long climb back out of the sun's gravity well. Now, gravity, which had been pulling it in, was now trying to pull it back, to slow it down. It's like throwing a ball straight up into the air. Gravity slows it down until it stops and brings it back. But if you throw the ball fast enough, at what's called escape velocity, it will never stop and fall back. It will just keep going, slowing down but never stopping, forever escaping Earth's gravity. Oumuamua was moving so incredibly fast that it was well above the sun's escape velocity. The sun's gravity succeeded in bending its path, acting like a gravitational slingshot, but it could not capture it. So, as it flew away, it began to slow down, but it was slowing down from an unimaginably high speed. It was like a car slowing from 200 miles per hour to 150 miles per hour. It's still going insanely fast. By the time it reached the distance of Earth's orbit, it was still moving at a breathtaking clip. Its closest approach to our home planet occurred on October 14, 2017, when it passed about 15 million miles away. Now, 15 million miles sounds like a huge distance, and it is. It's about 60 times the distance between the Earth and the Moon. We're safe from any object at that range, but on the scale of the solar system, it's a hair's breadth. It's a very close shave. Consider that Mars, our neighbor, can come as close as 34 million miles. Oumuamua passed us at nearly half that distance. It was a true near miss by the standards of interstellar distances. And here lies the great irony, the bittersweet twist in the story. This once-in-a-lifetime event, the first ever visitor from another star, had its closest encounter with Earth and made its daredevil loop around the sun a full month before we even knew it existed. We were completely oblivious. By the time Robert Varick spotted its faint speck of light on October 19th, it was already on the outbound leg of its journey, already saying its goodbyes. It was receding from us at an ever-increasing rate, getting fainter and fainter with every passing hour. We caught it as it was waving from the departing train, not as it arrived at the station. This timing had huge consequences. Because it was already so far away and moving out so fast, our window to observe it was heartbreakingly short. Within a matter of weeks, it had faded beyond the ability of even our most powerful telescopes to see any detail. We had to scramble to learn everything we could in a very brief period. We were like archaeologists who had just been told a unique, ancient artifact had been unearthed, but it was already being washed away by the tide. We could only grab a few quick photographs and measurements before it vanished into the eternal night, a silent ship once more, carrying its secrets with it. Its grand tour was the ultimate whirlwind visit, a dramatic entrance, a blistering dash through the inner solar system, a close pass by our world, and a rapid, silent exit, all before we even had a chance to properly say hello. The frantic race was on to learn everything we could about this visitor before it vanished forever. The world's most powerful telescopes, including the legendary Very Large Telescope in Chile and the Keck Observatory in Hawaii, swiveled to lock onto it. What did they see? The first surprise was its appearance. When we think of objects from the cold outer reaches, we often think of comets. As comets approach the sun, their ices heat up and turn directly into gas, erupting from the surface and creating a beautiful glowing cloud called a coma, and often spectacular tails that can stretch for millions of miles. Oumuamua showed no coma, no tail. It looked like a bare, inert asteroid. This was puzzling. It had just come extremely close to the sun, yet it showed no signs of outgassing. This initially led astronomers to classify it as an interstellar asteroid, a chunk of rock. The second surprise was its bizarre shape. Astronomers determine the shape of distant objects by watching how their brightness changes over time as they rotate. A spherical object has a steady brightness. A lumpy or elongated object gets brighter and dimmer as it presents its wider and narrower sides to us. Oumuamua's light curve was dramatic. Its brightness varied by a factor of 10 as it spun. This meant it was incredibly elongated. Early estimates suggested it was perhaps 10 times longer than it was wide, a shape like a cigar or a needle. Later analysis suggested a more pancake-like or oblate shape, but one that was still radically more elongated than any known asteroid or comet in our solar system. Imagine something the size of a football field, but shaped like a cigar, or perhaps a flat, thick wafer, tumbling end over end through space. That was Oumuamua. This strange shape immediately fired imaginations and led to all sorts of speculation about its origin. The third surprise was its color. By analyzing the light reflecting off it, astronomers determined it had a reddish hue. This is actually quite common for objects that have been baked by cosmic radiation for billions of years in the outer solar system, like many Kuiper Belt objects. This space tan suggested Oumuamua's surface was ancient and had been thoroughly irradiated during its long interstellar journey. But the biggest surprise of all was yet to come. As astronomers continued to meticulously track its position, they noticed something almost imperceptible. Its path couldn't be perfectly explained by gravity alone. As it traveled away from the sun, it was accelerating slightly, just a tiny bit more than the sun's gravity alone could account for. It was experiencing a tiny, non-gravitational acceleration. This is something we see in comets all the time. The rocket-like effect of gases jetting out from the comet's sun-warmed surface gives it a little push. But Oumuamua had no visible coma or tail. So what was causing the push? This was the central mystery of Oumuamua. How could something behaving like an asteroid, no visible gas, be accelerating like a comet? This is where the plot thickened considerably. Let's pull up a chair and really unpack this fascinating part of the story, where the scientific detective work gets truly intense and the imagination soars. We've got this object, Oumuamua, that's already broken all the rules by being our first interstellar visitor. But then, it starts breaking even more rules right here in our own backyard. It's like a guest who shows up unannounced, which is surprising enough, but then they start behaving in ways that defy all explanation. They're not eating the food. They're floating slightly above the chair, and they keep glancing at the clock in a way that suggests they can see time itself. The combination of its weirdness, its origin from the great beyond, its lack of a dusty comet tail, its bizarre tumbling cigar or pancake shape, and that final, baffling kick of acceleration it got as it was leaving, created a perfect storm of mystery. It was this combination that inevitably and understandably led some of the brightest minds down paths of truly exotic speculation. The most famous, and let's be honest, the most thrilling of these exotic explanations came from a well-respected astronomer at Harvard University, Professor Avi Loeb. Now, Professor Loeb looked at the same data as everyone else, but he asked a different kind of question. He focused on that non-gravitational acceleration, that little extra push. He reasoned that if it wasn't visible gas doing the pushing, what else could it be? One known force in space is radiation pressure. This is the tiny, tiny push that light itself can exert. It's not much, but if you had a giant, incredibly thin and lightweight sail, a light sail, it could theoretically catch this light from the sun and use it to propel itself, much like a boat's sail catches the wind. Loeb suggested that perhaps Oumuamua wasn't a natural object at all. Perhaps it was a piece of advanced alien technology, a discarded light sail from an interstellar probe, or even a derelict spacecraft itself, its engines dead, but its vast, thin sail still catching the solar wind. He pointed to its unusual shape as being ideal for a sail, and its brightness suggested a reflective surface, which fit the idea. It was, he argued, the simplest explanation that fit all the very strange facts. Now you can imagine how the media reacted to this. Harvard astronomer suggests alien probe visited solar system is a headline that pretty much writes itself. It exploded across news sites and social media. It was thrilling. It was the story we've all been waiting for since the first science fiction book was written. It tapped into that deepest of human curiosities. Are we alone? And the idea that the answer might have just zipped through our solar system, noticed only by a few astronomers before vanishing forever, is the stuff of both dreams and nightmares. It's a compelling, powerful narrative. However, and this is a crucial part of the scientific process, the vast majority of the scientific community met this idea with intense skepticism. And this skepticism isn't about being closed-minded or boring. It's about a fundamental principle of science, famously stated by Carl Sagan. Extraordinary claims require extraordinary evidence. Claiming an alien spacecraft is an extraordinary claim. It's the ultimate claim. The evidence for it would need to be absolutely rock solid, undeniable, and eliminate all possible natural explanations first. The scientific method is like a courtroom. The burden of proof is on the person making the claim. A light sail was a fascinating possibility, but it was still just a hypothesis, and one that required leaping to a conclusion far beyond what the available evidence strictly demanded. So, how do you look for evidence of aliens? Well, if it were a probe or a piece of technology, maybe it was sending out signals. Maybe it wasn't entirely dead. Scientists immediately pointed the most powerful listening devices on Earth towards Oumuamua's last known position, the Green Bank Telescope in West Virginia, one of the largest and most sensitive radio telescopes in the world, spent hours listening intently across a wide range of frequencies, searching for any whisper of an artificial signal, a carrier wave, a pattern, anything that sounded like it was engineered. The result? Nothing. Only the natural, silent hiss of the cosmos. There was no chatter, no beacon, no leak of alien radio. It was, as far as anyone could tell, utterly, completely inert and silent. This didn't disprove the alien hypothesis. Maybe it was just dead, or we were listening on the wrong frequencies. But it removed a key piece of evidence that might have supported it. The silence was deafening, with the alien hypothesis lingering as an unproven but exciting what if the real work of science began. The challenge was clear. Find a natural, physical phenomenon that could explain all of Oumuamua's weirdness, especially that invisible push. The gauntlet had been thrown down, and two particularly elegant and compelling theories emerged from different teams of researchers. The first theory came from scientists Alan Jackson and Stephen Desch. They started by thinking about what kind of material could provide a strong pushing force when it vaporized, but wouldn't create a lot of visible dust. Dust is what reflects sunlight and creates the bright coma and tails we see in comets. So they needed a volatile ice, a substance that turns directly from a solid to a gas, that was very powerful but left little dusty residue. Their search led them to nitrogen ice. Now, where do we find nitrogen ice? Right here in our own solar system, on the surface of Pluto and Triton, a moon of Neptune. It's a common material in the cold outer reaches of planetary systems. So, their idea was this. Imagine a distant Pluto-like world in another star system. A gigantic impact, perhaps with another large object, shatters this dwarf planet. A shard of its nitrogen ice crust is hurled out into interstellar space with tremendous force. This shard, which they proposed Oumuamua was, is then sculpted by its long journey and by its close pass to our sun. As this nitrogen iceberg approached the sun, the heat began to vaporize the ice, but in a very specific way. Nitrogen ice sublimates, turns directly to gas, very cleanly. It wouldn't kick up a lot of dark dust or complex organic molecules. It would just release invisible nitrogen gas. This jetting gas would act like a natural rocket engine, giving Oumuamua that precise, measured push. Furthermore, nitrogen ice is extremely reflective. It's about twice as reflective as a typical comet. This was a key insight. If Oumuamua was made of such reflective material, then to appear as dim to us as it did, it had to be much smaller than previous estimates. Jackson and Desch calculated that it could be a flattened object, not a cigar, but more like a cookie or a pancake, roughly 45 meters by 44 meters, and only about 7 meters thick. As it got closer to the sun, the vaporization would have smoothed and flattened it even more, like a bar of soap being worn down in the shower, explaining its strange shape. This theory provided neat, natural explanations for the acceleration, the lack of a coma, the shape, and the brightness, all using chemistry and physics we understand from our own cosmic backyard. The second major theory came from researchers Jennifer Bergner and Daryl Seligman. They took a different approach. What if Oumuamua started out as a completely ordinary, water-rich comet from its home system? Its journey, however, was anything but ordinary. For millions, perhaps billions of years, it drifted through the deepest, coldest voids of interstellar space. During this long journey, it was constantly bombarded by cosmic radiation, high-energy particles zipping through the galaxy. This radiation, they proposed, was doing fascinating chemistry deep inside the comet's icy body. The powerful cosmic rays were smashing into the water ice, H2O, breaking the molecules apart and releasing hydrogen atoms, H. This hydrogen gas couldn't just escape. It became trapped, frozen in place within the crystalline structure of the remaining water ice. Think of it like a cosmic sponge becoming saturated with hydrogen. Then, this sponge entered our solar system and made its close dive past the sun. The heat wasn't intense enough to cause massive, dusty outgassing like a normal comet, but it was just enough to warm the ice up a little. This warmth caused the ice to change its structure slightly, and in doing so, it squeezed the trapped hydrogen gas out. It wasn't a violent jet. It was a gentle, steady fizz of hydrogen escaping from the entire surface. Because hydrogen is the lightest element and is invisible to our telescopes, we wouldn't see it. But even a tiny amount of this gas pushing against the incredibly small and lightweight object would be enough to provide the exact amount of acceleration that was observed. It was a beautifully simple and generic explanation. Oumuamua wasn't a weird alien. It was just an old irradiated comet that had been storing gas for millions of years and finally belched it out when it got warm. A cosmic sponge, getting a cosmic squeeze. Both of these natural theories are now considered by many scientists to be strong, plausible explanations for Oumuamua's behavior. They show the incredible creativity of scientists when faced with a puzzle. They don't require us to rewrite the laws of physics or invoke unknown intelligences. They use known principles in new and clever ways. The debate between these ideas continues, and without being able to take a sample or get a closer look, we may never know for sure which one is correct. But that's okay. The most important lesson from this chapter of the story isn't about finding a single answer. It's about the process itself. It demonstrates the beautiful, self-correcting engine of science. A strange observation leads to wild ideas, which are then tested against evidence and challenged by more probable natural explanations. Oumuamua forced us to think, to innovate, and to better understand the weird and wonderful objects that might be drifting between the stars. It reminded us that the universe is capable of creating natural wonders strange enough to rival our wildest science fiction. The window to study Oumuamua was heartbreakingly short. Let's sit with that feeling for a moment, the true weight of what that short window meant. In the grand, slow-motion timeline of astronomy, where projects are planned for decades and observations can take years, the story of Oumuamua was over in a frantic, breathless flash. It was like trying to study a rare, beautiful bird that suddenly streaks past your window. You get a gasp, a glimpse of its color, a sense of its speed and shape, and then it's gone, vanished into the forest, leaving you with nothing but the memory and a desperate desire to have seen more. The race to understand it was a global scientific sprint. From the moment Robert Barrick confirmed its impossible path, observatories around the world, and even those in space, scrambled to point their lenses at this fading dot. It was a coordinated act of cosmic curiosity. Every second of telescope time was precious. Astronomers had to cancel their previously scheduled observations, sacrificing their own projects for this once-in-a-lifetime opportunity. They worked through the night, analyzing data in real time, sharing findings across continents in a frantic, open collaboration. They were trying to grab every single photon of light reflecting from this object before it winked out for good. They measured its spectrum, trying to read the chemical fingerprints in its light. They tracked its rotation with meticulous care, piecing together its bizarre tumbling motion. They measured its brightness with extreme precision, trying to understand the properties of its surface. But all the while, they were fighting a losing battle against the most relentless force in the universe: distance. With every passing hour, Oumuamua was getting farther away, and because of the way light works, its brightness didn't just fade in a simple linear way as it receded. It faded with the square of the distance. This is a cruel law of physics for astronomers. It means that if an object moves twice as far away, it doesn't become half as bright. It becomes a quarter as bright. If it moves 10 times farther away, it becomes 1/100th as bright. Oumuamua was already faint when it was discovered. This mathematical reality meant it was vanishing from our view at an accelerating, heartbreaking pace. Within just a few weeks, by mid-November of 2017, it had dimmed beyond the practical limit of even our most powerful Earth-based telescopes. The giant eyes on the ground, like the Very Large Telescope in Chile, or the Keck Observatory in Hawaii, could no longer gather enough of its fading light to form a useful image or take a clear spectrum. The final pictures were just a faint smudge, a ghost of a signal against the noise of the cosmos. The last chance was the Hubble Space Telescope, orbiting above the distorting effects of Earth's atmosphere. Hubble, our most faithful sentinel in space, managed to track it for a little longer, perhaps a few more weeks. But even Hubble's powerful gaze has its limits. By early 2018, just a few months after its discovery, Oumuamua had faded into complete invisibility. It was no longer a thing we could see. It had transitioned from a physical object we could observe to a set of data points, a collection of numbers and equations in a computer database. It had become a memory, but its journey, of course, did not end. It simply sped on, silent and unseen, following the immutable laws of motion and gravity. Let's trace its path outwards. After its close pass by Earth in mid-October, it continued its outbound journey. It sped through the asteroid belt, that ring of rocky debris between Mars and Jupiter, though it was far beyond any of those asteroids by then. It passed the orbit of Jupiter, that giant king of planets, perhaps in early 2018. Jupiter's gravity, so massive it shapes the entire solar system, would have barely registered as a whisper on Oumuamua's path. It was moving too fast, too directly to be swayed. It continued on through the realm of the outer gas giants, Saturn, Uranus, Neptune, though it didn't pass close to any of them. Its trajectory was taking it on a high-speed express lane out of the solar system. By now, it is far, far beyond the orbit of Neptune, the last of the official planets. It is sailing through the Kuiper Belt, a vast, dark, donut-shaped region, populated by icy worlds like Pluto, Haumea, and Makemake, and countless smaller objects, all remnants from the solar system's birth. But Oumuamua is not one of them. It is a foreigner passing through this territory, moving at a speed those native icy bodies could never hope to achieve. It is utterly, completely invisible to us. There is no telescope conceived by human science that could possibly spot it now. It is a dark, silent traveler once more, just as it was for eons before it met us. Its future path is set. It will continue on its way, moving inexorably towards the outer fringe of our solar system, towards a region known as the Oort cloud. The Oort cloud is a theoretical, spherical shell of icy objects that is believed to be the true outermost boundary of the sun's gravitational influence. It's a place of profound darkness and cold, where objects are so spread out and so distant that the sun is just a particularly bright star in their sky. Oumuamua will pass through this region in the coming centuries, and then, finally, it will cross the ultimate threshold. It will leave the sun's gravitational embrace entirely and re-enter the true interstellar medium, the empty, lonely gulf between the stars. It will not come back. Its path is what we call an open orbit or a hyperbolic trajectory. It is a one-way ticket out. The sun's gravity bent its path, but it never captured it. It's like a stone skimming across the surface of a pond. It touched the water, was deflected, but continued on its way, never to return to that spot again. Oumuamua's brief flicker in our telescopes was a true once-in-a-lifetime event, not just for a human lifetime, but for the lifetime of our civilization. We were just lucky that our lifetime, the brief period in human history when we had developed the technology to detect such a faint and fast-moving object, coincided with its flyby. If it had passed us a century earlier or a century later, we would have never known. We would still be wondering if such interstellar visitors were even possible. This is the loneliest part of the story. We read a single, thrilling, confusing page from its book. We learned its name, Oumuamua, the Scout. We measured its speed, its shape, its strange acceleration. We debated its origins, its composition, its purpose. But we will never know the rest of the story. We will never know the world it came from. We will never know what cataclysmic event launched it on its epic journey. We will never know what wonders it witnessed during its millions of years of travel. And we will never know where it is going. Its journey is endless. It will continue to drift through the Milky Way galaxy, a silent speck in the cosmic dark. Perhaps, in another 100 million years, it might chance upon another star system. And if that system has a civilization with technology even more advanced than ours, perhaps they will spot it, and they too will wonder at this strange, silent visitor from afar. But for us, the story is over. The book is closed. The scout has delivered its message, that the galaxy is full of moving pieces, that we are not isolated, and has moved on forever. But Oumuamua's legacy is immense. It proved that interstellar objects exist, and that they can pass through our solar system. In fact, astronomers now estimate that there are thousands of such visitors within the orbit of Neptune at any given time. They're just too faint to see. Oumuamua was only visible because it came so close to the Sun and Earth. Not long after, in 2019, we discovered a second interstellar visitor, 2I Borisov. This object looked much more like a typical comet, with a clear and visible coma, showing that a variety of these objects are out there. Oumuamua was the first, the scout that proved the path was there. The study of Oumuamua has opened up an entirely new field of astronomy. We are no longer just astronomers of our own solar system. We can now be astronomers of other solar systems too. By studying these interstellar interlopers, we can literally hold up pieces of other worlds to the light, figuratively speaking, and learn about the building blocks and formation processes of planets around other stars. Is Oumuamua a fragment of an exopluto? Does that mean Pluto-like worlds are common in the galaxy? The questions it raises are profound. And the hunt is now on for more visitors. New, incredibly powerful telescopes are coming online, like the Vera C. Rubin Observatory in Chile. Its mission is to conduct a deep, relentless survey of the entire visible sky every few nights. It is expected to find dozens, perhaps even hundreds, of new interstellar objects in the coming years. Each one will be a new treasure, a new puzzle piece in our understanding of the galaxy. Oumuamua was the first proof that this cosmic treasure hunt was even possible. So, as Oumuamua continues its solitary voyage, it carries with it a new meaning. It is a symbol. It is proof that our solar system is not an isolated island. It is connected to the galaxy by a sea of drifting objects, fragments of other worlds, messengers from distant suns. It was a quiet, subtle, and mysterious scout, not the dramatic arrival we might have imagined, but in many ways, that makes it more wonderful. It reminds us that the universe is full of secrets waiting to be discovered, often in the smallest and most unexpected of packages. Its brief visit taught us to look at the sky differently, to expect the unexpected. And so, the next time you look up at the stars, remember that between them, in that profound darkness, countless other messengers are drifting silently. Oumuamua was the first to say hello. It won't be the last. And so our mysterious scout, Oumuamua, vanishes back into the infinite dark from whence it came, a silent teacher that showed us we are not an isolated island, but part of a vast, interconnected galaxy, forever exchanging material, and perhaps even the building blocks of stories across the light years. Its brief visit reminds us that the universe is still full of wonders we can't yet explain. And that's what makes the great cosmic story so beautiful. The search continues. The sky is full of secrets, and who knows what we'll discover next. Thank you so much for journeying with me into the depths of space tonight. If this story of our first interstellar visitor helped you relax and wonder, please let me know by giving this video a like. It helps more than you know. And if you haven't already, consider subscribing to Hafee Sleep and tapping that bell icon. It's the easiest way to ensure you never miss our next adventure into the mysteries of the universe. all designed to help you unwind and drift off. As always, I'd love to hear from you in the comments. Where are you watching from tonight, and what time is it there? Sharing that always makes our community feel a little more connected, no matter how many miles apart we are. From all of us here at Hafee Sleep, wishing you peaceful thoughts, sweet dreams, and clear skies. Good night.